Hello, I'm Sharwin Patel, and for my tutorial, I'll be showing how to implement the basic structure for behavior trees in Unity, as well as a patrolling character example, similar to how the enemy behaves in the Harry Potter game from the in-class assignment. In class, we learned how to implement a finite state machine to manage the behavior of an intelligent enemy. The FSM allows us to define states our game can be in and requires us to strictly define transition functions or cases between every state to other states. FSMs offer a really rigid structure and require the game state to be in exactly one state at a time. Transitioning between these states requires defined behavior to transition from a specific state to another state. With behavior trees, we have a bunch of nodes. We have different types. We have action nodes and condition nodes. Behavior tree is constantly being evaluated along with the runtime of the program and can behave differently based on conditional nodes. With the tree evaluation, a behavior tree uh, is constantly being evaluated, and every node is always returning one of three states, whether it's running, success, or failure. There's three core node types that a behavior tree operates on, and custom nodes can be created that are extended from these core three types. Action nodes perform some sort of action or tasks, like setting a game object's destination, for example. Condition nodes evaluate any condition, and if satisfied, allows the execution of that branch. Composite nodes contain several children nodes of any of these three types, and allows us to sequence child nodes together and prevents execution of that branch until all the child nodes are finished. In these next few segments, I'm going to walk through the code and explain the core structure to building a behavior tree. I'll also cover an example where we utilize our developed core to build a behavior tree for a patrolling object, traveling between waypoints and detecting enemies in the patrolling character's field of vision, and then traveling towards the enemy and attacking them. The core structure only contains four major blocks that can be abstracted to support any desired functionality. We have the base node class, a sequencer and selector, otherwise known as AND and OR gates. And in other examples, a node may be further abstracted to represent an action node, a condition node, or a composite node. But in this case, we're going to keep it simple and just implement the nodes as we need them, extending from our base node class. The node class is our base class that simply maintains its parent, a list of children, and its current state. Like we talked about before, a node has to be in one of three states: running, success, or failure. When the node is constructed, we add all of the children. To this node, and then also set the parent to this node. The node class has a virtual evaluate function that automatically sets to failure if it's not implemented. The evaluate function is where we expect any implementation or functionality to be written for whatever node class we write. For the action and condition and composite nodes, the evaluate function is where we write our functionality that interact with game objects or deal with any game logic. Next, we have our AND and OR gates, our sequence and selector nodes. The sequence node is our AND gate, and it also extends the node class. In the evaluate function, we utilize a switch case to determine if any child nodes are still running, and only return success once all children return success. The selector node is an OR gate, and this also extends the node class. Here in the evaluate function, we again use a switch case, and it looks very similar, except this time, if any child node has succeeded or still running, then we return that respective state. Otherwise, this node fails. Finally, we have our tree class. This is really simple. All this does is it allows us to build our tree using an abstract function, and then in the update function, this tree is constantly evaluated. Notice that the tree is abstract, but also extends mono behavior, and so this allows us to actually create a game object that has this tree, and then this is what we put our behavior inside of. For our example, we need to create a few nodes to embed the desired behavior into our tree. If we consider our objective here, we want to do three main things. We want to have our character patrol, which is kind of an action node. We want to have our character check if there's an enemy in its field of vision, which is like a condition node. And then finally, we need a third task to travel to the enemy once the enemy is in our field of vision. Again, this one is an action node. Here we have our implementation. So for the patrol task, we actually we take in a lot of data here, and all of our functionality is embedded in the evaluate function. All the references to the game data that we need are passed in through the constructor, and some have default values in case we don't necessarily need to set them. Inside the evaluate function, all this node does is essentially travel to a waypoint, or it waits at a waypoint, depending on some timer. And then it transitions between every waypoint and keeps continuing. Note that this function always returns running, and because traveling or patrolling doesn't ever necessarily succeed or fail. Next, we have our condition node, our is, enemy, and FOV. This node, essentially, in its evaluate function, will either succeed or fail, hence the nature of a condition node. And this essentially uses the same logic as our Harry Potter game, checking for the Dementors within our field of vision. We find the direction to the enemy. We find out if it's in our field of vision and if the raycast is hitting it. And if so, then the enemy is in our FOV. This function, again, takes in some references and game data in the constructor in order to perform its logic. Next, our final task, our go to enemy task, is very similar to our patrol task because we're simply just moving the character towards a target transform. Here, there's just some extra functionality to destroy the enemy after some time once we wait there. This is to simulate attacking. Finally, we have our player behavior tree class. This is where we actually create the behavior tree, and this is the script that is attached to the game object of our player. We need to extend the tree class and implement create tree, where we return the root node with all of our nodes within. The root node is the topmost node, and the priority of each node decreases as we go down and add them. So in our tree here, we combine our condition node and our task to go to enemy node using a sequencer, which is like our AND gate, and then we OR all of these together with our patrol task. Note that the patrol task is all at the bottom, so this means that it has the least priority. So if the sequence is returning success because both of these are succeeding, then this is going to execute before our patrol task does. So if we switch into Unity now, there's a couple of important things here. First, because of our logic, we use player and enemy tags, and so we have to make sure all of our enemies have our enemy tag. Next, all of our waypoints are tagged, are not tagged, but are created and then added to the player. So inside of our player behavior tree, we go back to the code real quickly. This is actually where we define all of our data that we actually pass into our nodes that each node needs in order to perform its behavior. All of these are public so that we can implement these in the inspector, or we can edit them as the program runs, and then all of them are passed in wherever necessary. Coming back to Unity, our player, which is our green cube here, has some value set for it. And then additionally, we have the enemy transforms list set up with our 3 enemies. And then we have our waypoints added to our inspector as well. So if we run this, we're going to see some debugging output, and we're going to see our behavior in action. So you can see it's traveling to the waypoints. It's waiting at the waypoints. You can see the FOV of the player. You can see the radius. You can see once it finds it, it goes, the blue radius is the stopping distance, and then it continues on its way. So now, if we go back to the scene here, you kind of see him moving around. We want to get to this enemy, but it's not inside the FOV. And so let's go ahead and grab this waypoint. Let's see, how close do we have to move this guy? Just a little bit. So we'll actually move this right here. Kind of move this so it comes in at an angle where it will see the object. And now you'll see as soon as it's in the range, it'll go, it'll stop, it'll delete it, and then it'll go on its way.